please give Gav a round of applause.
Cheers. Thanks. So I've got two talks, and I'm not sure which I should do. So I'll have a show of hands. So one of the talks is primarily around Polkadot, its governance in general, and a little bit about one of the protocol features that's quite new. The other is a talk on the Substrate that I made kind of for today, but doesn't really say very much if everyone's familiar with the runtime. Basically, it goes over the runtime modules, what they do, and also talks about some ideas for the chains that might be built on it. So, show of hands for people that want a talk primarily on Substrate and the runtime modules. Okay, around 50%. Let's see where this is going. And for those who are more interested in governance and Polkadot. Yeah, all right, 50%. Yeah. So how should we decide this? Okay, so I guess I'll kick off with the Substrate talk and maybe try and cram both in. I've actually got quite a big slot, so I can probably do both talks. Okay, so can everyone read that? It's not very bright. Anyone having trouble reading that? I tried to keep the font big, but I'm not convinced that's like super legible anyway. Okay. So yeah, this talk, as I mentioned, is sort of going over some of the high-level things of Substrate. I think perhaps not everyone here is super confident or knowing all about the general modular architecture of Substrate and the Substrate runtime. So I'm going to talk a bit about that. So the architecture is not, particularly crazy. There's this is a diagram that's been going around for a while, but basically there's the consensus stuff, which is a big part of Substrate, and then there's a WebAssembly engine, and then stuff gets executed within WebAssembly. We call that stuff the runtime, which is maybe a bit of a misnomer, but hey ho, it's kind of stuck now, so we've got to put up with it. So the runtime is coded in Rust, but it goes, at the moment at least, but it does get compiled down to WebAssembly, and it gets run inside this interpreter. And it's the thing that executes all of the business logic of the blockchain. So the architecture is a bit like an apple in that we have three kind of levels of abstraction to Substrate. We have the core, which is kind of like this. And then we have the module library, the SRML, the Substrate Runtime Module Library, which is a bunch of independent modules that each have business logic that addresses one particular aspect of functionality that you might want running on a blockchain. And then on top of that, we have Substrate Node, which collects together these basic SRML modules into a single kind of definitive blockchain client. And that can be used to kind of do whatever that you want to do with a blockchain if you don't want to like change any internal logic. But this talk's going to focus on the second layer, the SRML sort of layer of this apple. So I'm going to talk about those modules that you can compose together. So an SRML runtime SRML is basically the modules that go inside this runtime circle here. So it's the modular core of your chain. And it amalgamates a number of different things that a runtime, that's useful to have in a runtime. So calls, these are basically dispatchable closures, right? So they're things that can be called. Functions is perhaps what we normally call them. The key thing here is that they're dispatchable, which means you don't have to sort of hard code which call you're going to do at compile time. You can store it in a kind of functor object as a reference to a call, and then you can just use this reference to call. And these functors can be serialized into, for example, a transaction. So inside your transaction, you can place an identifier which can be sort of dispatched along with some, again, serialized parameters for that call, and you'll end up actually making this call inside the runtime. Alongside calls, which are actions, you've also got storage, which is state. So calls can basically read from the storage. And together these two basically form the notion of what we would sort of typically call kind of object orientation, object-oriented programming, where you've got your methods and functions or whatever, and you've also got your internal storage. Now we've got some additional things that are useful specifically for blockchain and in sort of blockchain business logic coding. So origins are, in essence, they give you a part of the system that has actually dispatched a particular call. Yeah. So whenever a call gets dispatched, it gets dispatched from an origin, and the origin, in essence, encodes a notion of privilege. How privileged was the caller when they dispatched this call? So if the call is like, for example, transfer some balance, then an origin can be this particular account. Yep. So this particular account transferred some balance, great. Then that's the account that we have to reduce before we increase someone else's. An origin can also be something privileged, like the super user or root origin, and that's the sort of origin that can do crazy shit like reset the entire runtime or arbitrarily change pieces of the storage. So origin is a little bit like, on Unix, who am I? It's like the user, so to speak. Events are the kind of opposite of calls. So calls, you sort of tell the runtime what to do. Events report on what the runtime has done. This microphone's kind of crappy. Have we got a better one? It keeps crackling. Cheers. Hello? Hello?
It takes a little while for it to kick on.
Are we on? Yeah, okay. Right, so yeah. Events report on particular things that have happened in the runtime, and they get stored so that it can be later queried by, for example, the user interface. Logs are a bit like events, except they actually get placed in the block header, which means they're very efficient for light clients to query, but that's kind of beyond the scope of what I want to talk about right now. Inherents are basically a way of oracleizing data. Is it just that speaker? Okay. They're a way of oracleizing data from the environment that is creating the block author, onto the chain. So inherents are, in essence, a way of collating information that is available to the block author and then kind of encoding it as part of a transaction that gets placed on the chain and therefore allows you to make the bridge between information that's known to the block author and information that's only available to on-chain logic. And finally, it amalgamates the JSON configuration, which allows modules to specify what it is that the user should provide in creating a Genesis block. So, for example, block time might be, well, indeed is one of the parameters, and I think the timestamp module can specify what that block period should be. And it does that through stating that it should be a configuration element within a JSON file that the user would provide as part of their chain specification. So, without further ado, let's get into the modules. Oh, I really dislike this. I didn't realize it was one of these like click for every line jobs. Okay, so balances is the first module I'm going to go over. This gives you an account-based currency. So account-based, it's not like Bitcoin, it's not like the UTXO stuff. This is much more like Ethereum. So each account has a balance associated with it. When you send funds from an account, that balance will go down. When you receive funds, it goes up. We actually have a number of traits, so a number of kind of interfaces that this implements. currency, lockable currency, reservable currency. So these are basically various different kind of types of currency. It implements all of them. It also implements transaction payments, so you can use the balances module as a way of specifying how transactions should be paid for. Aside from like lockable and reservable currency, which are kind of interesting things in and of themselves, this also supports vesting and existential deposit, which I want to sort of explain a little bit. So vesting allows you to have vesting schedules from Genesis. So when you, what I mean by that is different accounts, if they get endowed funds in the Genesis block, then those accounts can be kind of locked, or those funds can be locked, not spendable, but can become increasingly spendable over time, yeah, until eventually it's all spendable. So vesting as a similar manner is used in companies, particularly startups. ED, existential deposit, allows us to mitigate the problems of dust accounts. So this is a big issue on Ethereum. It bloats the state horrendously. Basically, for some minute amount of value, you can keep a particular account, force the network to retain information on a particular account. And that means that if you have organizations, companies that systematically create these dust accounts, like many of the exchanges do, then you just have systematic bloating of the chain. So what we say with the balances module is that any account, for the system to bother even retaining information on an account, there must be at least a particular amount of funds in it, and we call these this minimum amount of funds the existential deposit. Now, the existential deposit isn't the lowest unit that Substrate can handle. It can retain the difference between a balance of the existential deposit and a balance of the existential deposit plus one tiny itsy bitsy little unit, right? That itsy bitsy little unit can be much, much lower than the existential deposit. But what it means is that if the balance ever drops below the existential deposit, even by one tiny little unit, then it will be deleted, yeah? So once you go above existential deposit, you have the full precision of the currency. But below existential deposit, you have 0. So it's literally just the minimum amount that can be stored in an account before it gets deleted. So indices. Indices are something that, as far as I know, haven't been implemented within other blockchains, but it is sort of an idea that's been floating around for a while. Basically, it's a short-form account identifier. So cryptocurrencies will typically have lots and lots, particularly ones like Ethereum, will have lots and lots of accounts stored on them. Now, each of these accounts tend to be referred to by their public key or by an address that's derived from their public key. Usually, so in the case of Bitcoin and Ethereum, you take the public key and then you hash it, and then you might drop some of the data of the hash, because the hash probably is overkill for identifying any individual account. So the hashes that Bitcoin and Ethereum use tend to be about 32 bytes. With Ethereum, we actually drop 12 of those bytes, and account identifiers are just use 20 bytes. But still, 20 bytes is quite a lot of space. So what account indices do is they say, right, every single account in the system that has some balance in it, right, that has something in it that we're storing some state of, we're also going to store an index, right? And as new accounts come along, we store additional indices. We make up a new index for them. So we start at 0 and we sort of just work our way up. So what if you run out of indices? Well, we've got 32 bits worth or 64 bits worth of indices. And in reality, there's only like a few 100,000 of these accounts that are going to exist within the first 5 years. So it's not going to be a big issue. But what it allows us to do is to use the short form index. So rather than putting the whole 32 bytes or 20 bytes public key or account ID in there, we just store the index, which is generally going to be 1 or 2 bytes big. And so, as you can see in this image, we can take a relatively large key and actually replace it with a much, much smaller key. Kind of useful. So the timestamp module allows us to basically oracleize the wall clock time onto the blockchain. A lot of chains I think basically all of them, automatically oracleize it because they keep the timestamp as part of the header. But Substrate, in an effort to be minimal and abstract, doesn't do that. If you want timestamp, you include the timestamp module, and that puts it in. The session module facilitates session keys. Session keys are basically the keys that validators or authorities on the network use in order to identify themselves, to sign statements, to sign blocks, generally to interact at the second by second, block by block level. We want these to be different to their account keys, the things that are holding funds or identifying them long term, partly because, well, they might get compromised short term, so you want to keep them on rotation, and partly because you don't want to necessarily have these long-lived keys probably called. You want to ensure that they stay called rather than sort of go into the client and be used like super hot and potentially open to attack. Session module itself at the moment only supports a single key. We use those for authoring the blocks, but in the future we'll support an arbitrary key tuple that can be basically kind of configured at the point that the runtime is amalgamated together in that central lib.rs file. Session ensures that these keys only change on session boundaries, so it retains any key changes up until the boundary point and then has them all change at the same time. Next module is the staking module. So the staking module is one of the most complex modules in Substrate. You don't need to worry about this if you're just doing a POA chain where the authorities sort of either don't change at all or do change, but change only with particular, when the authority set or some super user declares that they should change. Staking allows you to select an authority set based upon economic principles if you're happy that there's a currency that's valuable on the chain. It works with any lockable currency implement. So Balances implements lockable currency. Balances module is perfectly compatible with staking, but in principle other modules can be as well. It really just has to implement this trait. Staking module is very, very configurable. You can have a look at it, see how configurable it is, but I don't really want to get into the specific options here. It implements the NPOS, nominated proof of stake algorithm, which is sort of mostly developed now. It's I think there's like 1 or 2 minor changes to go in, but otherwise it's finished. The thing about NPOS, if you're not familiar already, is that it splits nominators from validators. So the validators are the ones that actually validate, that run the nodes, sign messages, and ensure that the chain stays live. Nominators are just the ones that lend their capital to these validators and ensure that basically these guys are economically incentivized to not misbehave. NPOS has both both rewards and slashing on the balances that are locked, and it also, as I say, ensures that these balances are locked in order to mitigate against any long-range, nothing at stake style attacks. You can find more information in the staking module itself, but that's a rough overview. So the next one is Sudo. Sudo is very, very simple. It's a key privilege certificate. So it's the very simplest form of governance. It's basically a dictator. The Sudo module retains a key, an account identifier, which is able to basically have its privilege elevated up to sudo, and therefore do anything, up to super user, and therefore do anything on the system that it wants. It's useful for testnets, but in principle might also be useful for like a POA chain where you don't really care about governance, you just want the ability to upgrade it from a central point. Democracy module is the sort of core of Polkadot governance, and probably one of possibly the most complex runtime module in Substrate. So democracy is a privileged referendum dispatcher. What do I mean by that? Well, privileged dispatcher, which is to say it can dispatch calls across the runtime. So basically it can call any sort of exposed dispatchable function in any Substrate module, any runtime module. And it can do so with super user privileges, right? So it can do so essentially from this ultra privileged point, which means any of these calls that do potentially do damage to the system, democracy can in principle execute. Now, it does so based upon the results of referendums. So democracy is a little bit tongue-in-cheek. It's not really a democracy, but it's, let's say, more democratic than a lot of things. It's based around the lockable currency trait. The lockable currency trait, as I mentioned before, it's implemented by balances. Lockable currency is different to currency in that it just lets you, bloody hell, it just lets you kind of lock up option, have your currency, have your balance locked up for some period of time. Democracy requires this for some of the functions that I'm about to talk about. So the first thing is it's got like priority queue proposals. So this is the idea behind this is that public, the sort of general transaction masses can place proposals. Proposals are just dispatches, right? They're just basically kind of transactions that require a privileged origin. Yeah. So an example of this would be like set code. So set code is the thing that you can use to upgrade your runtime. It won't execute unless it comes from a super user origin. So these proposals, these sort of suggestions for privileged dispatch calls, go into a queue, and the queue is prioritized based upon the amount of balance that's backing this proposal. You can, when you place a proposal, you put a minimum sort of backing down. You don't get this back until the thing is actually executed. If it never gets executed, you never get it back. So it's like don't put this don't put proposals in lightly. As time wears on, these proposals are sort of taken out of the queue and with the one that's got the most backing one at a time, and then dispatched. Well, no, not dispatched, then put to the vote. So what do we mean by put to the vote? So the voting mechanism within democracy is kind of fairly sophisticated now. So it kind of started off a bit similar to coin voting. Now it's somewhat different. So I'll talk a little bit about how it's different. So the first thing is it's not coin voting, it's lock voting. So coin voting, when you vote in a sort of typical coin voting system, then the amount of voting power you get is proportional to the amount of funds that sort of are in your account, at least at some point or another, generally at the point that the vote actually goes through. That's kind of the same here, but also there's a multiplier applied to it, which is how long you're committed to holding these funds for in the system. The longer you're committed, the bigger the multiplier. So if you commit yourselves for like 4 weeks, then you get twice as much voting power as someone who only commits themselves for the minimum 2 weeks. The reason there's a 2-week minimum is because we have this notion of delayed enactment. So it takes 2 weeks, or I should say, this is like the Polkadot parameterization, but in principle, these are just parameters that Substrate, you can parameterize as you want within the Substrate module. But as I say, within this sort of basic period, we'll say 2 weeks for now. Even if the approval passes, even if the proposal passes and gets approved, it doesn't get enacted until some point later, until after these 2 weeks, allowing for those who didn't approve of it to take their funds and go elsewhere. So you've got this kind of, I've heard it called rage quit in the context of Moloch DAO, but basically you've got an ability for those who lost within this referendum to move out and avoid having their funds sort of locked in to this change that they didn't want. It's got proxy and delegation voting. These are two different things. Proxy voting is very simple. It's where you say, I'm not going to vote with my funds, but I want this other account to vote with my funds, right? But from this point on, you should not consider this account to be able to wield any voting on behalf of its funds, but rather only this other account should be able to do that, and it can do that as much as it wants. That's proxy voting. Delegation voting is a much more general system, which is where you have this kind of multi-level, I'm going to delegate my voting activity to this other person, and maybe someone else will, maybe there'll be hundreds of accounts that will delegate themselves to this other account, and then that account might then delegate their voting onto some other account, and eventually end up with this huge kind of hierarchy of voting where everyone wants to have the opinion of the sort of parent node. And you end up with like one massive grand ancestor that can vote with everyone's funds. That's much harder to do. It's all off chain. There's a few other sort of cost benefit advantages, disadvantages between which one you choose. Proxy voting was meant primarily for when you want to keep your funding key, the key that actually is able to transfer the funds, entirely cold. So you stick it on a paper wallet, put it in a safe somewhere, never use it. But you want a separate voting key. So proxy voting allows for that specifically. Then the final thing is the adaptive quorum biasing modal approval. So this allows the approval mechanism to change mode based upon basically how this priority made its way to referendum, and it uses this technique called adaptive quorum biasing in order to specify how the votes should be counted and what an approval looks like given yes votes, no votes, and some total population size. I'm going to go into these things a little bit in more detail in the next talk, if assuming there's time. So I don't want to dwell on them too long here. Council is the same. I don't want to dwell on it too long, but basically it's a secondary governance body that you can optionally have. You don't have to have it. You can just have the democracy body if you sort of want something simpler. Again, it's currency based. It uses a rotating approval vote, which I'm going to go into next. And it provides a new origin. That's kind of interesting. So origins are not like hard coded. You can have modules that introduce new origins and then use them in other modules that want to accept dispatches or want to allow their functions to be dispatched only if it comes from some logic in this that claims to be from this other origin. The Treasury is exactly one of those modules, so it actually uses the council origin for approving and rejecting proposals, but anyone can put in proposals, and it's really just a way of provisioning funds that sit in a sort of pot with some degree of oversight. In this case, the oversight is with the council module. I think the final one I'm going to talk about is contract module. This provides WebAssembly smart contracts, as you might guess. It has a few interesting pieces of functionality that you'll already be familiar with to some degree after the talk yesterday. It does resource tracking, so basically gas counting. It executes them in a sandbox so that they can't mess around with the state of the runtime itself. It allows these sandboxed execution things to dispatch calls in the runtime. So you can call into and do interesting stuff like transfer balances and whatnot. Potentially also put yourself forward for governance or vote or whatever. It allows you to call into other contracts as you would be as you'd expect with Ethereum sort of environment. And it has I've called it enlightened state rent because the state rent that we're implementing doesn't require rent to be paid outright. You can pay your rent simply through sort of hodling tokens. And this means that for usages like wallets, like multi-sig wallets, you don't need to worry about the balance always going down over time or having to pay for this thing. Simply by storing funds in the wallet, you'll be sort of paying for the state there. The other thing that we want to put in, it's not in yet, but it will be in the not too distant future, is user account storage. This is basically to avoid, to mitigate the situation where you have contracts like ERC20 contracts that have huge amounts of state on behalf of vast amounts of users. So basically the storage footprint of the contract increases as more and more people use it. And really what you want to do is have the user pay for their individual slice of the storage. You don't want the contract to have to pay, rent the state for the entire, for the whole lot of it. And this functionality would allow that. Okay, so features that we want to implement in the not too distant, or in the future at some point. Off-chain workers. So this is something that's sort of already partly in, but it's will be coming in to a larger degree in the not too distant future. This will allow you to use CPU, various resources on the nodes of the network. Initially, at least, the authority nodes, but eventually, basically any full node that's willing to sort of enable this particular feature. One of the interesting sort of ways that it could be used is with secure storage. So you can basically have arbitrary sets of workers store keys for you, and then come together and potentially combine these keys in order to sign some transaction or do something on behalf of a contract or runtime module. Another thing is indexable events. At the moment, our event system is pretty kind of basic. One thing that we want to bring in is the ability to index particular events, so that like clients and maybe blockchain explorers and whatnot can easily know when particular events have happened, be they balance transfers into a particular account, or governance actions, whatever it is. Fee abstractions, fees have been something that have been floating around. The sort of API for fees have been floating around for a while now. This is something that we will sort of increase and make better over time. Already we've got some fairly low-level abstractions, but eventually we want to introduce a fees module that will be optional, but still allow you to, if you want to use it, do things like split fees between block authors, the Treasury, burning it, and probably one or two other destinations, and allow different fees collected for different reasons to all be handled by the same bunch of logic. Another new feature that's being worked on is this Polkadot piggyback consensus, or Cumulus. It allows us to allow Substrate chains to use the Polkadot consensus rather than their own consensus, and therefore sort of piggyback on Polkadot's relay chain. I'm not going to go too much into that. Rob sort of covered it a bit in his talk yesterday. Probably one of the most exciting features for me is the on-chain parallelism, which isn't one that's super high priority, but probably is going to wait till version 2 or 3 of Substrate. But this is basically where we allow worker tasks to execute within the runtime. We have certain constraints to neutralize the possibility that they can be non-deterministic. So you've got to ensure that the runtime actually always executes in the same, or comes to the same ultimate result. So there's a few caveats, and a few things have to be worked out. But in essence, it's going to be possible to, where storage doesn't sort of interfere with the different worker threads, it's going to be possible to parallelize execution within the runtime itself. And certain modules will be changed in order to utilize this parallelism. Probably primarily the executive, which is the thing that actually executes the transactions, and the block constructor, which is the thing that figures out what the transactions are. We will probably add an additional like parallelization map so that it knows which transactions can be executed at the same time, and then it places them all into different workers accordingly and parallelizes them, executes them in parallel. Final thing I want to talk about in this little chunk of time is the chain idea. So ideas for like chains on Substrate, in Polkadot, whatever. So there's a few sort of obvious ones: smart contract chain, like the Edgeware guys are doing with the with our contracts module. Perhaps an EVM-based chain, although I think EVM's probably going out of vogue. Parallelized account-based chains. So I don't know if you've heard of them, but like the guys from the Blink protocol are doing one of these. So chains, it's a chain that has accounts similar to Ethereum. Only the individual accounts are handled by separate network actors that sort of act as mutexes. And in order to send stuff, or in order to do a transaction that uses multiple accounts, you have to sort of get a lock from across multiple of these mutexes, and you can like ultimately prove that you got your lock and you acted according to what you expected was sort of a synchronous thing across the network. And if ever there's any instance where something was executed essentially out of order, you can prove that you at least did it correctly, and therefore you can eventually punish whoever did it incorrectly, and therefore it is in some sense economically secure. It's quite nice because you end up with parallelism at the account level rather than at a shard level, so you don't have the issue of contracts that are, or accounts that are in the same shard being able to talk to each other quickly, but accounts that are in different shards not. So you got some kind of opaque potential distance between things that are apparently in the same network that doesn't need to be considered if you parallelize in this way. Zero knowledge proof chains. I mean, obviously, like a Zcash style ZK proof currency. There's actually there's a project I saw in Tokyo, a Zero Chain, that's already sort of on the road to building this. But in principle, depending on how far the rabbit hole goes with these kind of ZK snarks, ZK starks, and so on, it might be possible to introduce a kind of ZK stark contract chain, or even a ZK stark Polkadot chain, where the validators of Polkadot don't need to actually execute anything. They just check to make sure that the parachain was executed correctly by checking out this concise proof. That would be really cool, but it might still be several years off. That said, because we're upgradable, we can always bring it in later. Another one might be a transient chain hub chain. This is a little bit similar to like what the Plasma protocol is trying to do, but basically it's like a chain of chains. So a bit similar to Polkadot, except the chains that this would manage don't talk to each other, so you don't have that scalability issue, and they wouldn't live for very long. So they only live as long as it takes for their individual transactors to do their sort of accumulated transaction. So it's actually somewhere between a proper blockchain and a state channel. It's kind of like a state channel done as a blockchain, so it's like blockchain light. This is like really good for things like IoT, where you have devices that kind of want to do a short-lived set of transactions just between themselves. So they create a new blockchain just for themselves, do their transactions, and then eventually report back the result to the hub chain, so to speak. If there's ever like a problem, if one of the devices thinks that something's gone wrong and the other device isn't acting correctly, or there's a dispute or whatever, then basically you can take the entire blockchain back up to the hub, and it can execute and figure out what the correct thing to do is. Another one might be like an Oracle chain. So I think oracles haven't really been developed super far. I think there's an awful lot of a way to go. One of the interesting things might be a very generalized Oracle chain that's able to take a language, like a propositional logic language, similar to like, if we're going to go like all the way down this road, then we could take something like Lojban, which is like a well-defined, semantically unambiguous, natural propositional logic language. It's a bit, if you're not familiar, hands up if you heard of Lojban. Okay, like 7 people. Okay, so it's a bit like it's like the sort of nerdy version of Esperanto. So it's like this like created. It's an artificial language. Some guy created. It's not actually the original one. The original one was something else. I forget what. But it's like the open source version of this language that a professor created in order to make a Esperanto-like language that was, in terms of its grammar, unambiguous. So of course, for its semantics, it's a little harder to make it unambiguous because we're dealing with real-world concepts. But in principle, it's a relatively formal language for talking about things that happen in the real world, and making like an oracle chain that allows you to basically just pump out like machine readable but human understandable propositions about the world could be something that's kind of interesting to do, and then it would like potentially feed into economic, financial chains or whatever else you want to do with knowledge of the world. And then, of course, the obvious final one, like a homogeneous multi-chain, so a sharded piece of logic. Interestingly, one of the things I'm going to talk about in a second, assuming there's time. Oh, there's not much time. Okay, is kind of this, but people tend to know it of like at the moment as Ethereum 2.0 or Jasper or whatever. Okay, we're not going to go to questions. I'm going to like speed through this other talk, so hold on to your hats. Right, so governance. This is a talk on governance itself, why it's a thing, what it is, and I'm going to touch, but probably not very long because I don't have very much time, on governance in Polkadot. So what is governance? If you look it up, you'll find lots and lots of definitions, but the definitions generally have a few words in common. First thing is that they're rules, right? So it's a set of rules. Second is that it's about deciding stuff. So it's about adopting decisions. And third thing is there's usually some notion of like regulation or accountability. So accountable. So there we go. It's a system of rules to make decisions with participants being held accountable. In the context of technology, governance tends to have the decisions that we make tend to fall around standards. So it's about the changing of standards or protocols, right? So technology doesn't sort of really reduces the problem space a bit. Once you fall outside of technology, then it can be all sorts of random stuff. But since we're only really caring about technology, then we will welcome with open arms this reduction of the scope. So we can also say, like, in short, governance would be rules over the system rather than the rules within the system. So within the system, there are rules. We can place rules. We can say, right, when I interact with you guys under this context, then these are the rules, right? And that's fine. But governance doesn't need to worry about that because those rules are like things that I bring to the table. There's maybe some overarching rule set, but those specific rules don't need to be, there doesn't need to be any governance system messing around with those rules. Rather, the governance system is about the rules over the entire thing. So you can look at this as a little bit like governance doesn't need to worry about any individual contracts. Governance is about changing the law itself, the law books. And just as blockchain was once kind of made often equivalent to Bitcoin, right? I mean, if you go way back to like 2013, 2014, blockchain didn't really exist as a word. Like, people vaguely knew of it. But if you went to the conferences, it was Bitcoin conferences. If you did meetups, it was Bitcoin meetups. But blockchain isn't Bitcoin, right? We understand that, at least now. It's, or most of us do. I guess there's probably some people that still think they're more or less the same. And similarly, coin voting isn't autonomous governance. And there are sort of less enlightened people that will still attempt to equate coin voting and autonomous governance. And when I say autonomous governance, I kind of autonomous, on-chain, sovereign, whatever, but basically kind of proper governance. It's not coin voting. Coin voting was like maybe the first initial idea or the first initial implementation, but it doesn't. It's not where it ends. It's the same with the Bitcoin and blockchain. It might have been the first implementation or the first idea, the first use case, but it's not. It's not where it ends. So why do we bother with governance? Well, these rules over the system have to evolve. I mean, things evolve. The world changes. New technology comes in. The situation in which the technology or the product exists changes as well. Other products come muscling in, and it's important to be able to adopt and adapt and evolve into new and better things. As Darwin kind of vaguely said, survival of the fittest. You have to remain fit. So, in that sense, governance is critical. The ability to make coherent decisions is critical to ensure that the product, the blockchain, the system can evolve and continue to exist in a useful state. Now, if we couple this with the idea that like decentralized cryptoeconomic systems, by which I mean basically blockchains, but probably will be other systems as well. I mean, there are already people sort of exploring other ideas for what these decentralized cryptoeconomic systems could look like. They will probably become the new kind of states. And when I say states, I mean kind of like jurisdictions, countries, right? Kind of places that have their own fundamental sets of rules, from their architecture, their boundaries, their cell walls, divisible chunks of the internet of the internet economy. And if we follow the sort of this blockchain dream to the assumed end, then these things will become really important, like jurisdictions of the internet. You'll buy into them, and you'll like be based on them. Like these will be like the platforms that people use in order to conduct their lives online. And as such, it's governance. One of the things that it needs to manage is the relationship between these individual jurisdictions. In addition to the relationship between these jurisdictions, it will also be required, is needed in order to take whatever economic power that these, as I say, large swathes, these corners, these platforms of the internet have, and use them to further their economic interests, right? To further themselves. As sure as Facebook engages in various marketing techniques in order to push its platform further down the road, and as sure as Google does the same for its platform, and as sure as Twitter does the same for its platform, these new decentralized cryptoeconomic systems, these platforms of the internet, will need to do the same, and they will have a bunch of resources at their hand. They will have billions in market cap at their hand. Who knows, in 5-10 years' time, it could be tens or hundreds of billions that they will have at hand in order to push their system, push their economic incentives further. And governance is going to be crucial. Because they're decentralized, they can't rely on like getting a CEO or a board of directors to push it down the road. Well, maybe some can, but we won't go into that. Rather, we'll need decentralized means of making decisions, right? Decentralized governance. And without it, they won't be able to use those resources. So what about rough consensus? Well, rough consensus isn't really a thing. Rough consensus is a way of saying, we don't really want to deal with it. We quite like things as it is. And I'm kind of, I'm being a bit nonchalant, but it's if you implement. If you take rough consensus, the basic idea, and you implement it in a non-algorithmic manner, so you don't really implement it, right? You just have a general kind of feeling that, yeah, we've got consensus, or no, we don't yet have consensus. Then it's going to lead to either slow or non-existent decision making. There needs to be, a proper underlying process. That process should have certain limitations in terms of time for it to actually make decisions. Decisions need to be made. They cannot be put off forever. And rough consensus implemented in very vague ways, as it often is by the sort of people putting forward rough consensus as a solution, doesn't fulfill that decision-making criteria. And the other thing is that rough consensus doesn't really facilitate making the hard decisions. Rough consensus might be okay when you've got like a bunch of industry participants, and the goal is to make the least bad decision, or the decision that at least everyone there can just about live with. But that doesn't make great platforms. That just makes platforms that will retain some degree of the status quo of adoption. Oftentimes, the best change is not a popular change. Yep. We already were familiar with the notion of populist governments who do bad changes, right? They do popular but bad changes. Well, this is kind of the opposite of that. But the point is that the good changes are not necessarily popular, and similarly, bad changes may not necessarily be contentious changes. So why do we want autonomous governance? Why is it important to implement it on chain? Basically because, if you accept that autonomous financial contracts, or the autonomous execution of contracts, if you accept that autonomous payment mechanisms, autonomous currencies, if you accept that things that are rules-based should be executed in an autonomous fashion in general, then you must also accept that governance, being rules-based, by very definition, should therefore also be executed in a basically unemotional, amoral, almost like blind, but nonetheless logical fashion. Well, machines are that. They are impartial, they're efficient, and they're fast. Use them. So let's get back towards Polkadot and what Polkadot's doing. So I want to introduce you to the Metaprotocol model. Probably everyone's familiar with this model, but may not think of it in quite these terms. So the traditional model, like for example, Bitcoin doesn't have a Metaprotocol model. I have a very basic protocol model. So you've got a protocol, you have some nebulous crowd of indecision, so basically a bunch of different opinions. And then going forward, these opinions plus no Metaprotocol essentially gives you lots of different directions that you can take the protocol in. And ultimately, although we've only seen one fork of Ethereum that I know about, Bitcoin has demonstrated that, over time, these probably are going to lead to many different forks, some being more popular than others, but nonetheless fragmentation of the ecosystem. And without any way of these things working together, it sort of leads to ultimate reduction in value, or at least that's a not unreasonable assumption, I would say. On the alternative side, we've got a metaprotocol. So a metaprotocol says, well, the underlying protocol, the metaprotocol, never changes. So you never need to fork that. The nebulous crowd of indecision puts its opinions into the metaprotocol via the governance system, and then the protocol within the metaprotocol, which oversees the rules of how these opinions lead on to changes in the protocol, that forces that sort of upgrades or moves the protocol along in a deterministic, transparent, and open fashion. So basically, all of the people who had their opinions can see that their opinion was taken into account one way or another, and the protocol was moved according to the underlying rules, which they understand themselves. So it means that you've got a way of managing the contentiousness, the contention, and in some sense forcing some degree of compromise. So why, main sort of difference is, well, the traditional model doesn't require you to formalize your rules of change, right? The traditional model doesn't require any rules at all because, there are none. It's just like whatever you want, run whatever node you want, run whatever version of the protocol you want. So it doesn't require any formal rules up front, but it also means there's no way of guaranteeing that any process that you place upon the changes that should happen are actually respected. There's no way of ensuring accountability or transparency, at least not within the protocol. And therefore it leads to pretty much these kind of vague, dumb processes and personality-driven nonsense that we often see in these dumb blockchains. And you risk, stagnancy and so on. You also risk this kind of what I call a silent coup d'état, which is kind of what does it mean? It's essentially when there's an underlying decision maker of a system, but you don't understand that they're a decision maker because they're using sort of means and at their disposal to mask their influence. Now, that's because of the opaqueness of the system. This is possible. If the system becomes transparent, you can actually kind of see who the decision makers are. Then it becomes a lot harder to pull off. So with a meta-protocol, the rules must be formalized. That's the big disadvantage. You can't have a meta-protocol governance system unless you're willing to actually set the rules up front. If you mess up the rules, or if you don't know what the rules should be, then you can't use a meta-protocol. But if you're happy with the rules, then you get all these nice guarantees. So the processes can be autonomously enforced and executed. There's accountability. It can lead, because it's machine interpreted, machines can do fast things with lots of data. You can have really sophisticated and dynamic processes as part of the decision-making apparatus to change, to upgrade the protocol, or even to change the governance system. So your speed of evolution essentially goes up, and the sophistication by which evolution can happen can also go up, so you can start using things like market forces and so on. Of course, there is a risk. The risk in this case is that the rules are wrong, and you line yourself up for huge amounts of volatility, the protocol swinging one way and then another way, or just entire collapse of the system. The only thing that's worth pointing out is that all meta-protocols ultimately boil down to the same sort of traditional governance systems underneath, right? So the meta-protocol itself relies upon a sort of crappy traditional style governance protocol, which means if ever anything goes like dramatically wrong, you can still fall back on techniques like hard forks and offline manual consensus in order to put things back on the right track. So you never lose that. It's just you gain a bunch of autonomy. So in the context of an autonomous cryptoeconomic system, we can say that governance, well, the rules are going to be algorithmic and machine executable, absolute, they're defined up front, and the accountability is facilitated basically by signed transactions that go into the system. So you can check what each of the actors, each of the stake holders are doing and saying, and make sure everything adds up. So in summary, governance facilitates evolution, allows you to put economic resources of the system to use, and it shapes the external relations between these systems. When I say external relations, I would include things like, Polkadot relay chain. So you can take the governance of a substrate, an independent substrate solo chain could say, well, we want a closer relationship to these other chains, so we want to take our chain and turn it into a parachain. And the governance would be able to make that kind of decision. For a system like, well, let's say Bitcoin, I mean, that's a really bad example, but that wouldn't be able to make such a decision because it doesn't have any governance. It's kind of like a dumb actor in this space. And one of the things that I think we will see going into the future is that these dumb actors will either adopt some degree of governance, they'll manage to hop along because there's a sufficient amount of intelligent centralized governance, or they will die. There will not be sort of dumb logic blockchains existing indefinitely. These things, it's sort of like an unevolvable organism in a world of evolving, in an evolving world full of evolving organisms. It will simply become outfitted to the environment. Okay, so why is governance so late to the party? Well, basically, we're still immature, right? It's only 10 years since the first blockchain, and these things take 2 years at a time to develop. So really you've got to sort of get the core stuff done first, and upgradability and maintainability wasn't really a core thing. The core thing was like, cool stuff like smart contracts and treasuries and whatnot. But nonetheless, I think the time is nigh. We are moving towards that point. We're also seeing, I think if you'd have asked people in like 2013, in 10 years, do you think there'll just be like one chain ruling them all, like Bitcoin or whatever else? I think you would have found that a lot of people would sort of assume, yeah, basically there's going to be just one winner. I think that number is probably a bit lower now, although I don't have any statistics to back me up on that. And of course, the original thinkers of blockchain didn't think too much of inflationary monetary policy. You can see that just by the economics of Bitcoin. But basically, yeah, cohesive governance will be able to will allow blockchains to wake up as economic actors and do stuff as a whole, as a single-minded whole. So autonomous governance in Polkadot is based around stake-weighted referenda, council, and then also a treasury. I covered these modules earlier in over Substrate. So referenda allow Polkadot to evolve, right? Easy enough. So you can upgrade the runtime, you can change parameters of the runtime. You can poke arbitrary bits of storage if you need to fix some state. They can be started in 3 ways. Public referenda, which I mentioned the thing before, that's the priority queue where you can table things and the thing with the most, the proposal with the most stake behind it gets voted upon. But also through the council. A unanimous council and also a majority council can both put forward additional referenda. This is where we get the adaptive quorum biasing with positive and negative turnout bias. This is a way to mitigate the problem of low amounts of turnout potentially making a volatile decisions. Right? So basically what we need is a way of having a way of ensuring that if the turnout is low, we need a much greater approval before the proposal actually passes and gets enacted. And so we have this interesting formula. It's actually very simple. Do we have it somewhere? Yeah, here we go. So basically, if there's a unanimous council, then we have negative turnout bias. If it's a public referendum, we have positive turnout bias. And if it's just a council majority, then we have a neutral turnout bias. Positive turnout bias, what this basically means is if there's not very much of a turnout, you need an overwhelmingly large majority to pass something, right? As the turnout increases, then you need less and less of a majority until it gets to 100% turnout, at which point you only need a strict 50% majority. Yeah? So at low turnouts, you need an increasingly large supermajority. At high turnouts, you just need a basic, well, at the very highest turnout, you only need a basic majority. For negative turnout bias, we flip it. So at low turnouts, you need a high majority to prevent it from passing. Yeah? And then as you get all the way up to full turnout, you only need a strict majority to prevent it from passing. So basically what we say is that if there's a unanimous council decision that, this is a good idea, this proposal should be put through, then a lot of people need to turn up and say, no, we don't think it's a good idea before it actually doesn't go through. So it's still ultimately, the power is still ultimately with the stakeholders, but the default is biased one way or the other depending upon the opinion of the council. If there's only a council majority, but still a majority, then it's a neutral turnout bias and it's just whichever one, whichever side, yes or no, is bigger. Cool. So the council itself is a approval voted body. It's proportionally representative, more or less, based upon our latest algorithm. And basically one member of the council gets re-elected at a time. And the assembled stakeholders can place their stake behind any number of council candidates, and the one with the most votes gets one with the most stake behind them gets the seat. The runners-up get to keep by default, keep their votes for the next seat. So it really kind of, we're doing this to try and ensure that A, the council doesn't change all at the same time, it changes gradually, and B, there's a high degree of a churn within the council to try and ensure that the members keep changing or at least don't automatically stay the same. We also have this notion of unused votes staying around for the next election. So if someone gets elected that you didn't approve of, your votes actually get added on. The ones that were kind of unused because you didn't approve of the winner get added on for the next guy. And that means that we go from being not very proportionally representative to becoming more or less exactly proportionally representative. The more or less bit is because there's a small decay factor added on to it to prevent certain extreme circumstances. So the abilities of the council, as I mentioned, they're able to propose referenda. They can also veto proposals. So really bad proposals, ones that they don't think is, things that they think is actually dangerous, they can veto the proposal once. But once they've vetoed it, if it comes back again, they can't veto it again. So basically the council can use their position to try and either restrict the rollout of buggy proposals that bugs are found in later, but before they're enacted. But they can also use their power to say, hey, we really don't think this is a good idea. You guys shouldn't vote on it. Of course, if the legislature, if the assembled stakeholders continue, if they do it a second time, then there's nothing much the council can do. We assume that the ultimate power of the system should be in the assembled stakeholders. This doesn't go into one of the other interesting things, which is lock voting, but I'll probably get asked about that in the questions later, so I can go into it then. And I think we're probably out of time, so I can't really go into the trust wormholes. Yeah, but never mind. Okay, that's the talk. Let's move on to the AMA.